Hi everyone, and thanks for tuning in to the Bi-Fi PV Workshop virtual edition this year. Hopefully next year we can get back to in-person edition. My name is Jenya. I'm the CEO and co-founder of PV Evolution Labs, or PVEL. I'm excited to be talking to everybody today about all the various testing we've been doing on different bifacial technologies and different manufacturers, and presenting some of the data that we've gathered. First, a quick introduction to the company. We started about a decade ago in 2010, and we focus on reliability and performance testing of PV modules, PV inverters, and battery systems. On the PV module side, we've tested over 360 different bills of materials or combinations of different materials. We support our global downstream partner network. Over 400 companies are signed up for this, representing over 30 gigawatts of annual installations. The backbone of the PVEL service is our Product Qualification Program, or our PQP. This includes extensive reliability and performance testing that is standardized across all participants. We perform extensive testing on most manufacturers that are active in the US market today and support our downstream network by helping them evaluate the manufacturers and helping manufacturers get qualified technically for their approved vendor lists. It's free to sign up as a downstream partner, so please feel free to reach out to us and get signed up as a downstream partner. The PV module product qualification program sequence is listed here in this slide. It includes a number of stress tests in environmental chambers, thermal cycling, damp heat, etc. Performance testing such as pan files and IAM. These are things that are needed by developers and independent engineers to be able to accurately forecast the energy yield. And it also includes 1 year of field exposure, where we actually install and grid connect modules and monitor their performance in the field for year 1. It's intended to be a comprehensive program that every manufacturer participates in the same scope. Today we'll be talking about a number of results that we've been seeing on our bifacial bill of materials that we've put through this testing. Bifacial PV technology, as everybody here knows, have some unique considerations. The technology is quite similar in general, but there are some differences. STC flash test, of course, needs to be measured from the front and the back. The degradation from the front and the back can be different, with different physical mechanism actually causing the degradation. We measure front and back performance, backside performance before and after every test, including LID, LETID, etc., all the other tests as well. For the pan file testing, there is full bifaciality characterization, including the new standards for PMAX Bifi 100 and 200. In thermal cycling, because a PV module is out in the field absorbing some amount of light from the back, the short circuit current that the module will experience in the field when you add both front and back illumination is higher than just the front side STC short circuit current, so increased current is used in thermal cycling. This is in the draft 61215 standard. And on the field exposure side, when we install bifacial modules in the field, it's done on 2 different albedos. Albedo is the ground reflection, the magnitude of light that's actually reflected from the ground to hit the back. This is a fundamental metric when looking at bifacial performance in the field. So this shows a quick snapshot of what we've covered, what our experience is on bifacial PQPs to date. We have over 33 BOMs in the product qualification program from 14 different manufacturers. So what used to be a 60 cell or a 72 cell, and every booth at SPI more or less had the same modules, same form factors, have really bifurcated into a number of different technologies. we, just in our testing, have seen full cells and half-cut cells, a number of different wafer sizes. Of course, 182 millimeter wafers and now 210 millimeter wafers are starting to pick up steam as well. Different interconnect methodologies, 5 bus bar, 6 bus bar, 9 bus bar, and of course back contact. P-type and N-type wafers, glass modules and glass backsheet modules. Some of this testing was actually completed for last year's product qualification program as well. The specs are outlined here. As you can see, the number of different technologies and the variations in different technologies is increasing, and we kind of expect that to continue. So jumping into some of the results here, all bifacial PV modules have what they call a bifaciality factor. This is just the ratio of the front flash test to the back flash test. At standard test conditions, the back is typically a bit lower, ranging from 70%, 75% of the front. For some of the higher efficiency technologies like heterojunction, it can get up into the 90s. The actual performance based on our testing is actually lower than what we've seen stated on the datasheet by quite a bit. Here is 4 different types of manufacturers, 4 different types of modules, mixture of glass and glass backsheet, of half-cut cells and full cells. You can see pretty much across the board the bifaciality factors that we measure in the lab are several percentage points up to 10% lower than what was stated on the datasheet. This is a fairly straightforward metric to measure. We recommend this get measured. It's typically not a warranted value, so it would probably have to be a separately negotiated warranty addendum to guarantee a certain bifaciality factor out of the box. Of course, when the back degrades at different rates than the front, the bifaciality factor degrades as well. And we'll get into a bit of what we see there. This chart shows a number of different manufacturers going through the stress tests and how the front has degraded relative to the rear side degradation. The naming convention here shows that M is different manufacturers, B is different bombs, and S is just different samples, different modules. Typically, in thermal cycling, we see reasonably consistent performance from the front and the back. This is expected because thermal cycling stresses predominantly the solder joints or the interconnects, and those are not substantially different from the front and the back. UV exposure mostly is the same. Oddly enough, on one manufacturer, we did see substantial backside degradation when subjected to UV exposure. PID, definitely we see different performance on the front and the back pretty regularly. Some of the backside degradation can be fairly substantial, as seen here. And LETID, similarly, we don't have a ton of data on this yet, but we do see different performance on the front and the back. As I mentioned earlier, the physical mechanism that causes loss of performance is different on the front and the back. Can be different with PID. Static charge buildup or sodium buildup on the back surface of the cell can remove the back surface field, reducing the carrier lifetime in the wafers. That's just one mechanism. There could be others. So getting into some of the details across the different manufacturers, in thermal cycling, as I mentioned, we typically see pretty consistent results from the front and the back. However, there are some exceptions. With manufacturer 2, we actually saw a few modules improve in performance. This is not too common, but it's also not unprecedented to see performance increase. Sometimes the encapsulants can get more transparent through thermal cycling, kind of like an anneal, especially if they're under-cured to begin with. Interestingly, manufacturer 4 all the way towards the right-hand side, we saw pretty substantial differences between backside and front side degradation. However, the overall magnitudes are not too high, 2% versus 0.5%. on a relative basis, they're pretty different, but overall magnitudes aren't too high. As I mentioned earlier, with the UV exposure, typically the same, except for with manufacturer 1, seen here on the left, the front side degraded very little, and the back side degraded 8%, plus or minus. This will present itself as just a degrading bifaciality factor. So the degrading bifaciality factor is not typically warranted. Only front side STC performance is typical in your standard PV module warranty. PID is one that we see pretty consistently worse degradation on the back side relative to the front side. This is clear here, and some of the magnitudes here are pretty high, 30% degradation, 15% degradation on the backside. This would cause a very substantial degradation in the bifaciality factor. Not all P-type modules are susceptible to this, though. Not all modules at all are susceptible to this. We've also, in the 2019 version of our product qualification program, introduced a backsheet durability sequence. This was really driven by starting to see fairly substantial failures in the field. After about 5 years in the field in harsh conditions, the lower quality backsheets would start to get embrittled and crack and actually have openings in the back of the backsheet. This, in the field, in a utility scale power plant, folks started seeing, and in a residential power plant too actually, folks started seeing ground faults. So when dew in the morning settles on the modules are wet, that moisture can bridge the gap between the opening in the backsheet, the cracks, and the frame, which is grounded. It's also obviously a substantial safety hazard if you have exposed high voltage conductors. The challenge with backsheet testing is it's not that straightforward, and none of these modules were, none of this failure was captured in certification testing. All of the failed modules in the field had UL and IEC certification. Effective backsheet testing that replicates these cracks in the polymeric backsheets requires some cyclic testing that includes pretty much all of the stresses: moisture, ultraviolet light, and mechanical or thermomechanical temperature cycling. So we came up with this sequence here. It's now performed on all of the PV modules that are participating in the product qualification program. Some of the test results are seen here. The isovoltaic AAA backsheet is the most famous example. There are about 12 gigawatts of this in the field. You can clearly see right above the bus bars where you see these cracks starting to form. The reason it's above the bus bars, it's a little stress point. We've done quite a bit of work with DuPont developing this test. DuPont, of course, was leading the development of backsheet testing before PVEL jumped into it with their MAST test. We have tested clear Tedlar and saw no cracking and no failures in the clear or the non-clear Tedlar. In addition to the laboratory testing that PVEL does, that PVEL specializes in, we also operate a 10-acre outdoor testing facility in Davis, California. It's the old PVUSA testing facility. It's the first outdoor solar testing facility in North America. It was originally built in 1986. We took it over in 2011 to do commercial testing there, and we are now running our outdoor 1500 volt bifacial test bed there. You can see we have a number of manufacturers installed there. The installations are on 2 different albedos. We have white, as seen in this image here, and just a natural grass coverage. The white is about a 45% reflection or a 45% albedo. The grass is in the neighborhood of 15 to 20%. 1500 volt strings are also important, rarely seen in other test beds, but very important to capture the mismatch effects that you'd see with bifacial, which we believe are going to be higher than what you'd see with monofacial strings. Jumping to some of the results from our outdoor testing, it's interesting. We see two manufacturers clearly performing better than the other two manufacturers, and they're pretty close to one another. So it's unclear what causes this improvement in bifacial gains. What we see on the white is 10-11% for the higher performers, 8-9% for the lower performers. This is a fairly large swing, a 2% plus swing from manufacturer to manufacturer. So while you may feel like bifacial modules are all the same, they are clearly not. We also see interesting correlation to time of day. So on the grass or the dirt, natural covering, we don't see a very substantial difference between midday and morning. With the white artificial sheet, we see a very substantial difference between morning, evening, and midday. This is likely because of the reflection characteristics of the different ground surfaces. Just an interesting kind of side data point that we've observed in our outdoor test bed. Another interesting observation is the difference in operating temperature of glass versus glass backsheet modules. You can't say that one operates necessarily at a higher or lower temperature than the other, but you can say, based on our findings, that there is a higher or lower temperature depending on the level of irradiance. The glass modules obviously have a higher thermal mass, so take a longer time to heat up. The glass backsheet modules heat up faster, but also cool down faster. So an interesting finding, a 1% shift in operating temperature could result in measurable value to the project owner. And I don't believe this is being effectively modeled today. Thanks everyone for your attention. Again, my name is Jenya. I'm with PVEL, and you can feel free to reach out to us. Here is a quick disclaimer from the Department of Energy, which supported some of the work done in our outdoor testing facility on these 1500 volt strings. Thanks everyone.